Hi everyone. Today we'll be discussing the LeetCode problem of the day, power grid maintenance. So you're given an integer C which represents C powered stations which are uniquely identified from index 1 to index C. And these stations are interconnected by few cables which is given by the connections to the array where the array has U of I and V of I. That means the station U of I and V of I is connected. And initially all the stations are online and you are given few queries. So the first query is of type 1 comma x where uh, you have to do a maintenance check on the station x. So if the station x is online, then it only resolves the check itself. And if the station is offline, then you need to, the check is resolved by any operational station with the smallest ID in the same power grid as x. And if no operational stations exist, then you have to return -1. Like suppose we will take an example. We have a system like this. In this case, initially if all are operative and you want to check for the station 1. So since 1 is operational, 1 will only resolve the check. Suppose let's say 1 is not operational and we want to do the check for the station 1. Now, since 1 is not operational, we will check all the grids in all the other stations in the grid which are connected to 1. So in this, for 1, 2 and 3 are connected. So out of this 2 and 3, we will return the smallest ID. So this will resolve the maintenance check. And you have the second type of query where it is 2 comma x. So you will be given station x and you just have to make the station go offline. Suppose the query is like 2 comma 3, then that means the station 3 will go offline. And at the end, you just have to return an integer array which will store the result of the query type 1 comma x in the order. So for 1 comma x, we have the query. So whatever station which will resolve the maintenance check, that will be added in our answer. And for this type of query, we don't need to add anything to our answer. So let's quickly look at the first input. So we have a C equal to 5. So total 5 stations. 1, 2, 3, 4, 5. And we have few connections. So first is 1, 2. So 1, 2 is connected. Then 2, 3. Then 3, 4. And 4, 5. So all the stations are interconnected. Now let's see the queries. So the first query is of type 1 comma 3. So since it's of type 1, we go to the type 1 and do a maintenance check on the station 3. Also initially all the stations are active by default. So when we have this query 1 comma 3, the station 3 itself resolves the maintenance check. So 3 gets added to our answer. And next we have a query 2 comma 1. So this is the query of type 2. So in type 2, the station 1 should be offline. So the station 1 will mark this as offline. And we don't add anything to our result. Again, we have the third query, which is 1 comma 1. This is the first type of query, which is a maintenance check. So now we can see that the first station is offline. So we check the other stations which are connected, which are all these stations. And out of them, we just have to return the smallest value. So that smallest station will do the maintenance check. So in this case, 2 is the smallest. So we'll add 2 to the answer. After this, again, we have a query 2 comma 2. So 2 goes offline. Then again, we have a next query, which is do a maintenance check for the station 2. Since station 2 is not operational, we'll check all the other operational stations. So in this case, we have only these 3 stations connected to this 2, which are operational. And out of them, 3 is the minimum. So we'll add 3 to our answer. So the output is 3 to 3. Let's quickly check the second input as well. So we have 3 stations, 1, 2, and 3. And we don't have any connections. So it's not interconnected. And we have few queries. The first query is do a maintenance check for 1. So initially all the stations are active. So 1 resolves the maintenance check by itself. So we'll add a 1 to our answer. After that, we will make the station 1 offline because of this query 2, 1. So 1 goes offline. Then again, we have a query 1, 1. So we need to do the maintenance check for the station 1. And we see that station 1 is offline. So we try to see if any of its neighbors are online. But since one doesn't have any neighbors, we just return a -1. So maintenance check doesn't happen for this one. So the output is 1, -1. Now coming to the constraints, we can have at max 10 power 5 stations, and the connection's length will be at minimum of 10 power 5 or c into c minus 1 by 2. We have c into c minus 1 by 2 because we have total 5 stations. So total 5 into 4 by 2 number of connections can be made. So from this, you go to all stations. So from this, you go to the other all stations and so on. So this is the same as 5C2. So if we connect all stations to all of the other, like we add all the edges possible, we can have total c into c minus 1 by 2 number of edges. So he just gave this to say that we don't have any duplicate edges. And then the connections of I dot length is 2. So in this connections array, the row size is 2. So this is the station, one station and the other station. So these both are connected. And this is the queries. So the queries, we have total 10 power 5. And queries of I0 is either 1 or either 2. So since we have two types, so it is either 1 or either 2. And the next one is the station number. Now let's go the approach. So suppose we have all the stations which are interconnected. So we have something like this. So all the stations are interconnected. So 6 is connected to 3 via this path and so on. So in this case, initially all are connected. And suppose we disconnect this 3. And when we do it, the remaining active connections will be, active stations will be 1, 2, 4, 5, and 6. And to answer the query for the station 3, so out of all these values, we just have to return the minimum. So we can store this 1, 2, 4, 5, 6 somewhere. And whenever we have a query, we look into this thing and see what is the minimum of all this, and we'll return it. And suppose in the next query, we have something like, we have a query of type 2, 1, which means make this thing offline. So station 1 goes offline. So when that happens, we have to remove this one from our data structure. And next time, whenever we have a query, suppose on query 3 again, since 3 is offline, we check in this data structure what is the minimum value present, and that will be our answer. So to achieve this, we can think of using a tree set. Because in tree set, we can delete a particular node at any time. And also from the tree set, we can get the minimum value present in it. So initially, we'll add all these 1 to 6 values in a tree set, since all are active. Like we'll also keep a active array, active Boolean array. So initially, all will be true. And whenever we have to delete something, we have to make something offline, we make it false. So 1, 2, 3. So these two are false so far. 1, 2, 3, 4, 5, 6. So this is the setup so far. So next time when we have a query of doing a maintenance check for 5, so first we'll see if the 5th node is online or offline. If it's online, we'll directly return add this 5 to our answer. Suppose 5 is also offline. We have a query to make 5 offline. So first we mark 5 as online status as false. And from the tree set, we will remove the 5. So in tree set, it will only store the active online nodes. So next time when we have a query for the 5, we'll check in the tree set what is the minimum value, and we will get 2. So 2 will be our answer for the 5. So 2 will do the maintenance check for the session 5 instead of this. So this is the approach, but it is not guaranteed that only all the nodes will be connected in a single way. So we can also have something like this. So these 3 nodes are connected, and then let's say node 4 and 5 are connected, then node 6, 7, 8, 9, these are connected. So in this case, we need to maintain 3 tree sets. Why 3? Because we have 3 connected components in this configuration. So what we need to do is, first when we are given all the connections, we need to create those many number of tree sets that are connected components we have. So first we have this 1, 2, 3. So for this, we will maintain a tree set which will store this. And for this 4, 5, we'll maintain another tree set which will store only the active nodes of this component. And for this 6, 7, 8, 9, it is another connected component. So for that, we'll also create one more tree set. It will contain 6, 7, 8, 9. So we have created three tree sets. So the question is, where do we store it? So we can store them in a map. So we can create a map of tree sets and give each of the tree sets some ID. So the key is 1 and the value is this tree set. And for the next one, we can say this is the set number 2 and this is the value. For the next one, we can give the key as 3 and this has the value, this tree set. So we have created a map of tree set. Now all we need to do is, suppose we have a 7. So for the 7, we somehow need to know in which tree set we have to look. So 7 belongs to the 3rd tree set. So to do this mapping, we'll also create a hash map which has, for the first key, this first is stored in the first tree set. So the value will be 1. For the second node also, this value is stored in the first tree set. So for 2 also it will be 1. For 3 also we'll have a 1. For 4, you can see that 4 is stored in the second tree set. So for 4, we have value 2. For 5, we have value 2. 6, we have value 3. For 7, 3. For 8, 3. For 9, 3. So we'll maintain 2 hash maps. This is the first hash map, which will map the current node with the tree set ID. And this is the second hash map, where key is the tree set ID and the value is the actual tree set. So to do the queries, suppose we have a query, let's say 2, 7. That means we have to make the node 7 offline. So first, node 7, we'll see in which tree set it's present. So node 7 is present in the 3rd tree set. So we'll go to the 3rd tree set, and from this we will just remove the 7. So 7 gets erased, and 7 is also marked as offline. And next, suppose we have a query of form 1, 7. So that means we have to do a maintenance check for 7. So since 7 is offline, we need to check all the neighbors of it, and we need to find the minimum of it. So we get the neighbors from the tree set. So we just need to know where the tree set is present. We check in the hash map for 7. It has a value 3. That means 7 is present in the set number 3. Now we go to the set number 3, and in this set number 3, we have the value as the tree set. From the tree set, we will return the minimum value, which is 6. So which means for 7, 6 will do the maintenance check. So this is the approach. For each connected component, we'll try to maintain a different tree set, and also we'll map the each number with the associated tree set number. And when we have these type of queries, we'll go to the particular tree set and we'll just get the minimum value. And we might also get a case where suppose all these are offline. So this tree set will be empty. Now when we have a query saying do a maintenance check for 1,8. So first we'll see where 8 is present, in which tree set number 8 is present. So it's present in ID 3. So we go to the ID 3 and get a tree set, which is initially empty. So if it's empty, we'll just return the answer as -1. So this is the extra check we have to do. Now let's code the approach. So first we need to create a adjacency list for all these connections so that we can perform our DFS to find the connected components. So let's just create an adjacency list. And initially we need to add the empty rows equal to 0. Now let's iterate on the connections and create the adjacency list. Connection in connections. So we have added a edge from connections of 0 to connections of 1. And since it's a bidirectional edge, we also need to do the same thing from connections 1 to connections 0. So we have created the adjacency list. And now we just need to perform the DFS to fill the values. Also, like we discussed, we need 2 hash maps. One hash map will be the key is integer and the value will be the tree set. And we also need another hash map which will be used for the mappings. So this hash map is used to map the current node to the tree set in which it is present. And initially, let's start set number equal to 1 and let's perform a DFS. Also, to perform the DFS, we need to have a visited array. So Boolean visited size will be c+1. So initially, all are not visited. So we are just iterating on the nodes from 1 to c. And whenever it's not visited, so if visited of c equal to false, we will perform a DFS. And when we perform a DFS, suppose we are starting at 1. So when we perform a DFS from 1 and whatever the nodes we are able to reach from 1, all of them come under the same connected component. So that's why initially we have set the set number 1. And when we perform the DFS, we will pass the set number 1 so that all the numbers that are traversed in this DFS call will be put into the same set. So first let's create a tree set. integer set. And then let's just perform the DFS. So while performing DFS, you need to pass the current value and the adjacency list and the visited array, then set mapping and the set number. Let me quickly create the DFS function. Okay, we need to pass the adjacency list. Okay, first the number in the adjacency list. Then I think before that we are passing the visited array. Reset and then set number. Also, I think the mappings. Let me pass the mappings as well. Then set number. So whenever we enter the DFS, first we'll mark the current node as visited, and we need to add this node in our tree set. So set.add x, and also in our mapping, we will put the mapping as set number. And after that, we'll iterate on the neighbors of this current value, and if the neighbors are not visited, we'll continue our DFS call. So I equal to 0, I less dot. So this is the neighbor, which is adjacent dot get x dot get I. So if visited of current is equal to false, then we'll just perform the DFS. Let me just copy this. And the only thing that will change is the current value. Here we'll pass the current. So the DFS call is done. So let's quickly dry run and see for this input what happens. So first one is not visited. So we'll perform a DFS call for the one. So you will set one as true, and in your set, so this is a tree set, and in this tree set you'll add a one. Let me make it small. So in this tree set you'll add a one, and in the mappings, one is being put in the set number one. So one is the key, and the value is also one. And after that, one has neighbor 2. So 2 is not visited. So you call DFS for the 2. And the same thing, we set visited of 2 is true, and you'll add 2 to the set. And then 2 is mapped to the set number 1. And again, 2 has two neighbors, 1 and 3. So 1 is already visited. So we don't proceed for that. We proceed for the 3. So 3 is added in the set, and mappings.put 3 comma set number 1. So 3 is mapped to set number 1. After that, 3 has neighbor 2, so 2 is already visited, so the DFS stops. So when the DFS call stops, this is the set so far. So once we have the set after doing the DFS, we will put it in the map. So map.put set number comma set, and we'll just increase the set number plus for the next one. So this is the other map. So key is 1, and the value will be the set we have created. And now set number is incremented by 1. So set number becomes 2. So in the next iteration, we are at I equal to 2, but I equal to 2 is already visited, so we skip. Next, I equal to 3 is also visited. Then we go to I equal to 4. Now 4 is not visited. So again, we create a new tree set and we start the DFS. So in this DFS call, first 4 will be added. Now 4 has a mapping dot put 4 comma set number. So for the 4, its set number is 2. And after 4, you go to 5. You add 5 in your set. And for 5, the mapping is also 2. And after that, the DFS stops. So 4 and 5 is a connected component. Once the DFS is done, you will put the tree set so far in your hash map, where key is the set number, which is 2. The value is the set you have just created, which is 4 comma 5. And your for loop continues. 5 is already visited, so you skip it. Now you are at 6. So again, you will start a DFS and the same process repeats. So 6 will be added here. 6 has a tree set 3. So again, previously we had set number increment, so set number now becomes 3. 6 is added, same with 7. 7 set number 3, and also 8. 8 also has a set number 3. And the DFS is done. And finally, we'll put this thing in our map as well. So this is the configuration so far. After doing the DFS, we have created this map, which is the mappings, and also another map to store the reset values. So once this is done, all that's left is to perform the queries. So let's just add it on the queries equal to 0 less than queries.length. So first we have type equal to queries of I 0, and we have the station number is queries of I and 1. Now type is of 2 types, either 1 or 2. So let's classify that. So if type equal to 1, we have to do something, then else the other. So for type equal to 1, we have to do a maintenance check. And for type equal to 2, we have to make it go offline. So let's first deal with the type equal to 2. So if type equal to 2, suppose let's take an example. We have 2 comma 7. So in this case, the 7th station should go offline. So the first thing you'll do is for the 7, since all are online, you first make it offline. I think I also have to create this one. Boolean online. It's an array. New yeah. So initially all the nodes are true. So when we have this type of query, the first thing we'll do is make the node offline. So we'll mark it as false. And here we can just say that online of x equal to false. After doing this, we also need to do another thing. We need to go to the set where this 7 is present and we have to delete it. So to get the set number, we can use the mappings. Mapping.getX. So from this mapping, we can see 7 is mapped to the third set. So set number will be equal to 3. So you got the set number. And once you have the set number, you can easily get the tree set from this map. Set equal to map.get set number. So from this map, you got the tree set, which is this 6, 7, and 8. So from this, all you need to do is set.remove x. So from this value, 7 gets removed. Now let's see the type 1 query. So in the type 1, first we need to check whether the current node is online or not. So if online equal to true, so if it's already online, then you'll directly add this in your answer. I think we also need to create an answer. list. Yeah. So if it's online, you directly that particular node only resolves the maintenance check. So otherwise, if it's not online, then we need to check in the connected components, which is the smallest one. So for that, again, we can get the set number from the mappings. So when we have the set number, we can easily get the set by doing map.get set number. So now we need to check the corner case where this set might be empty. So if set dot is empty, then answer.add -1. And if it's not empty, then answer.add set.first. So set.first will return the smallest value in the set. Again, let's take an example. Suppose we have 1,6. So first we'll see whether 6 is online or not. So 6 is online, so we'll directly add 6 in our answer. Let's see for other case. Suppose we have 1,7. So now we see that 7 is not online. So we go to the else case. We first get the set number. So set number is 3. So from this 3, we get this set, which is 6,8. And the set is not empty. So from this, we get the smallest value. Set.get first will give us the smallest value, which is 6. So 6 gets added to your answer. And finally, at the end, you can just return your answer. I think the return type is integer array and not an array list. So we need to convert this to an array. Let me just do it quickly. New int dot size result of I equal to answer dot get of I and return this. Let me test it. Okay, there's a semicolon there. And next one, this L should be capital. Okay, what else? Hashpap H is again capital. BOOLEAN, Boolean. Okay. Test case is passed. Let me submit. Okay, we have a runtime error. Let's see why we are getting it. I think the issue here is while checking, we are checking for the visit of C. So this should have been visit of I. So if the ith node is not visited, then we perform the DFS for it. Let me submit again. Yeah, now it works. Finally, let's do the time and space complexity analysis. So for the time complexity, first we are adding the edges, and then here we are performing the DFS. So the DFS will take order of n, and while performing the DFS, we are also adding it in our set. So this will take logN operation. So this entire loop will take n logN time. And after that, we are processing the queries. And for each query, again, we are trying to use the tree set. From that, we are getting the values, or we are removing the values from the tree set. So addition or deletion from the tree set is again logN. So this loop has a time complexity of q logN. So total time complexity, we have order of n plus q logN. And now coming to the space complexity, we are creating an adjacency list. And the size of the adjacency list can be at max the n square, the number of connections, which is bounded by minimum of 10 power 5. And also we are creating this hash map and the mappings, and these sizes can be at max equal to the number of nodes. So total complexity will be order of c square, or we can say order of n square. But here he have guaranteed that the connection's length will be less than equal to this. So the space complexity will fit. It's not exactly n square. We can say n plus c square, where c is the number of connections. And I also have the code in Python. If anyone wants to view it, I'll add this in the description as well. And let's catch up in the next video.